Okay, welcome to this lecture on phase diagrams. Let's open with just a slide that reminds us some things that we've seen on mixing metals in their solid state. So in the copper-nickel system, we know that nickel is fully soluble in copper at any composition, and likewise, copper is always soluble in nickel to any composition. Okay. And to highlight the reasons why you might do this, we can look at the results of making such a mixture as far as the tensile strength and ultimately the ductility, which is represented by the full percent elongation at break. Okay, so how does the tensile strength vary as a function of increasing weight content represented by the weight percent of nickel in copper? So over here at the first x-coordinate of the graph, we have pure copper, and we see that the tensile strength is just above 200, maybe about 210 megapascals, and that is the tensile strength for pure copper. At the upper limit, up at 100, we have pure nickel as a material there, and we see here that the tensile strength for pure nickel is something like 350 megapascals. And so when we start making mixtures by increasing the content of copper in pure nickel, or increasing the amount of nickel in pure copper, we start to increase the tensile strength by accessing these substitutional solid solutions for the binary mixture of copper and nickel. Okay. Similarly, we can look at the results on the percent elongation. And so again, pure copper is at left, pure nickel is at right, and those pure materials have similar percent elongation around 50% at the failure point. And as we introduce the complement metal, we start to decrease that percent elongation at failure and ultimately reach a minimum value here. So if it was your job to strengthen the material, making it capable of taking a higher amount of load, the highest data point on the stress strain curve, you would find that roughly 60 weight percent nickel would be desirable. So clearly there's some interesting morphology inside the material that might explain this. And so we want to learn more about that using a phase diagram. Okay, so you've already looked at phase diagrams in a one-dimensional sense, where you know from as early as high school most likely, or even elementary school perhaps, that as you increase the temperature of water, you can trigger phase changes. So a very simple phase diagram for that might be this. We stay in the solid state, that is the ice state for water, as we consider temperatures that are below 0 degrees C. And then ultimately when we hit the 0 degree mark, we will transition water into its liquid state. And that'll be the same as we raise the temperature of that liquid until we ultimately reach another transition point that is 100 degrees C, where the liquid water now turns to liquid gas. You know this phase diagram, and the most important kind of data we have are right here, which represent the phase transition points. And these are known and very specific to the conditions of the experiment, meaning the pressure. So at atmospheric pressure corresponding to 1 atmosphere, we have those two data points. And so the question might be, how do the position of these data points shift as we consider higher pressure conditions, like increasing in depth in the ocean, or going to lower pressure conditions, like climbing to the top of a mountain? Where do these phase transition points, or melt or boil points, go as a function of changing pressure? Okay. So a more complete phase diagram for water that shows how pressure influences those boil points is shown here. And so the red lines represent the boil points, for example, where we knew the boil point at 1 atmosphere was at this x position. And if we start dropping the pressure, we start to reduce the x-coordinate for the boil point. So we walk the transition for the liquid to the vapor state to lower and lower values if we drop the pressure. Similarly, we knew that the the melt point for water at 1 atmosphere was here. And as we start to increase the pressure, going to deeper and deeper locations in the ocean, that this melt point, starts to decrease in temperature to lower values. So the lines on here represent all the options for the melt point shown here or the boil point shown here. And ultimately they intersect at a common place called the triple point, where if you were able to hold the conditions of the material at about 1/100th of an atmosphere pressure and 0 degrees C, you would access water coexisting in 3 different phases of ice, water, and steam. Okay, at conditions lower than that, for example, conditions where you might cross from low pressure to low temperature, you can go from solid ice straight to the steam state, straight to the gas state of water. Okay, so crossing over these phase boundaries becomes an important thought exercise. And again, they represent kind of the boil point, melt point, or even sublimation point that you might observe depending on the pressure. Okay, so to give us some additional terminology, let's establish that so we're armed, ready to look at more complex phase diagrams. So we have components, so we're going to use this as the definition. So a component is the elements or compounds which are present in the alloy. Okay, so it could be aluminum into copper like we have down below, nickel into copper like we saw a moment ago. It could be tin into copper to make brass, for example, or zinc into copper to make brass. Okay, and what are phases? Phases are going to be physically and chemically distinct material regions that form. Physically means they're located in different locations, like we see black areas separated from gray areas. And chemically means they have a different arrangement in the packing of atoms or the bonding of those atoms. So in this diagram, electron micrograph of aluminum and copper, we see that 2 phases exist. One is represented by the lighter phases and one is represented by darker phases. They're in different locations and have different contrast and would therefore have different chemical bonding and arrangement of all the atoms in this case that are metal, aluminum, and copper. Okay, so it is possible to access a material that has 2 phases. In this case, one that is the alpha phase and one that is the beta phase. So in an atomistic view, it might look something like this, where, for example, we could have an alpha phase that's housed as a tiny little particle or area or puddle held within a matrix of the other material. For example, that could be the beta phase of the material. So this might be a model for what things look like in the 2-phase system for this mixed aluminum and copper alloy. Okay, so let's look at a phase diagram that's more reminiscent of things you've probably seen. So here is the sugar-water phase diagram. And you've likely experienced much of this at around room temperature when you look and experience drinks that are sugared or sweetened. And so we can use this phase diagram to teach us where we might access the syrup state for sugar and water. So we'll define the syrup as the liquid solution where we have sugar fully dissolved into water to make a homogeneous solution where disordered water molecules host randomly sugar molecules throughout. Okay, and you'll see that there's another territory on this map where if we have too high a sugar content, that we will see 2 phases coexisting. So we'll see a liquid phase that is not pure water, but is still liquid consisting of water with dissolved sugar, and that coexists with pure solid sugar that did not dissolve. Okay, so the x-axis in this map is the composition. What is the weight percent of sugar in the material of interest? Okay, and so thinking about materials that we've experienced around room temperature, around 20 degrees C, you might consider, what would happen if we started to add increasing amounts of sugar into pure water and walking that material to higher and higher x coordinate, that is building the composition of sugar to be higher and higher in concentration, represented by a weight percent value of that sugar. Okay, and so ultimately, you can see here that this phase diagram would teach us that we have a solubility limit where only so much sugar can be dissolved, where we eventually transition the mixture from a syrup to a two-phase domain where we have liquid and solid sugar coexisting. Okay, so the blue line, of course, represents the solubility limit across a variety of temperature conditions that we have labeled here. So the solubility limit here is the maximum concentration for which only a single phase solution can exist. It helps us define that. Very good. So maybe looking at that exercise, see if you can use the phase diagram here to determine what the solubility limit is for sugar at 20 degrees C, and pause the video if you need a moment to do this calculation and answer the multiple choice question here in your mind. Okay, so hopefully doing that, you saw and considered walking your way over to the intersection point between the isothermal parallel to the x-axis line of 20 degrees C, meeting with the solubility limit on the blue line, and we want to answer the question with respect to the weight percent, that is the x coordinate for this intersection point. And of course, that's going to be not quite 70, but somewhere between 70 and 60. So probably the best answer there is 65 weight percent. So 65 weight percent is the answer. Good. So in sum, if we're at 20 degrees C and the concentration of sugar is below 65 weight percent, we know and can expect a homogeneous sugar mixture. If we make a mixture that is higher than that, that is the concentration of sugar is greater than 65 weight percent, we can expect a heterogeneous mixture that is syrup and pure sugar. Okay, so we can use these phase diagrams to understand other processes that we might execute in our homes or in the lab. So let's consider an example where we travel from point A to point B. So we start with a mixture that is represented by the coordinates that is room temperature, and we have 70% sugar. Hopefully you would predict that we have two phases, syrup and sugar at point A, and as we travel up along the path from A to B, that is, we are increasing the temperature but maintaining concentration the same, that eventually we would cross the phase boundary and move across the solubility limit, and then render the material no longer two phases, but one phase as we cross the blue line, and ultimately achieve the final condition at point B, which was our 100 degrees C condition. Okay, so this is something you perhaps already know. If you wanted to dissolve more sugar into syrup, you might try to add that solid sugar and warm the solution to cross the solubility limit, that is our phase boundary. Okay, what about another thought exercise here? As we move that mixture at point B at elevated temperature, that is one phase, liquid syrup, and we start to add more sugar, so that is increase the amount by weight of sugar in that material, will eventually cross the solubility limit yet again and access a two-phase system even though we are at higher temperature, but now too high in sugar content for full solubility. Okay, so that would be accessing two phases, syrup and pure sugar. Okay, So if you recall, we would use things like the radius of an atom, the electronegativity, and the crystal structure to negotiate whether or not a solid solution could form. And so the Hume-Rothery rules would teach us that, and nickel and copper are in favor of full solubility. So we know that nickel and copper are totally soluble in one another for all proportions. And we now want to try to understand what the phase diagram might look like in that case.